Good day, students. Welcome to math.serve.com. In this group, we're going to be going over two examples to review the relationship between differentiation and integration. So we can basically see an illustration of the inverse relationship between the two operations. The instructions for the examples, we are to find the differential equation that the given equation is a particular solution of, and then we'll solve the differential equation with the given initial condition to verify that our generated differential equation is in fact correct. Okay? All right, so the first problem we're going to be looking at is number one, y equals 2x squared plus 3x plus 4. And the initial condition is y of 1 is equal to 9. Okay, y of 1 equals 9. All right, so let's go ahead and do the first part of the problem, which is to find the differential equation that this equation is a particular solution of. So what on earth does it mean for us to generate the differential equation? What we are going to do is simply differentiate this function, and that will give us a differential equation that this is a particular solution of, okay? So we're going to differentiate both sides. So if you differentiate this side right here, you're going to have dy dx. And then on the right side, if you differentiate 2x squared using the power rule, you're going to have 4x. And then if you differentiate 3x using the power rule, again, we'll just be left with 3. And the derivative of 4 is just 0. Okay? So this is the differential equation that this equation is a particular solution of. Alright, so let's go ahead and verify that our answer is in fact correct by using the inverse operation, which is integration. Okay? So verification. Alright, so to solve this differential equation or to find a particular solution, we're going to use a method called separation of variables. Okay, so you notice that here we have dy and dx. So we're going to separate our variables into dy and dx. So we can have our dy's on the left and dx's and the y's on the left side, and then the x's on the right side. Okay. Now you notice this dx down here in the denominator on the left side. We need it on the right side, so what we'll do is we'll multiply both sides by dx. So we're going to have the resulting equation is going to be dy equals 4x plus 3 dx. Okay? Now to solve for y, we have to find the antiderivative or the integral of both sides. Imagine as though there's a 1 here. So we're going to integrate this side of the equation and that side of the equation. Okay? The y tells us we're integrating with respect to y on the left, and dx tells us we're integrating with respect to x on the right. Okay? So when we integrate the left side, we'll have y equals, and then when you integrate the right side, you're going to have, using the power rule for integrals, remember if you're integrating x to the n dx, the antiderivative is x to the n plus 1 over n plus 1 plus a constant. Okay, there is a constant here also, but I'll tell you about that in a minute. So let's go ahead and apply the power rule for integrals here. If I apply here, this is 4x to the first power. So this is going to be 4x to the second power over 2. This 3 has a 3x to the 0th power. So when I integrate that, I'm going to have 3x to the first power over 1 plus a constant. Now this constant is a composite constant. It's a combination of the constant from the y and the constant from the x. So we just combine them together nicely to have that big C there. Okay? Because when we differentiate, that constant, the composite constant, will drop off. All right, let's simplify this equation. We'll have y equals, 2 goes there twice, 2x squared plus 3x plus c. All right, now we need to find the value of c. How do we do that? We're going to use the initial condition, y of 1 equals 9. So let's plug it in there to find c. So since y of 1 equals 9. Then we have, it just basically tells us that x is 1 and y is 9. So we're going to plug in these two values into this equation. So we have 9 equals 2 times 1 squared plus 3 times 1 plus c. Okay, let's go ahead and simplify that. We'll have 9 equals 2 plus 3, 5 plus c. Subtract 5 from both sides, you have c equals 4. Alright, so we plug the c back into our solution we have here. We're going to have the particular solution, y equals 2x squared plus 3x plus 4. Is this what the original problem was? Let's see. The answer is yes, so we're confident that our answer is in fact correct. Alright? Alright, let's take a look at question number 2. What if we have the equation y equals 3 secant x plus the natural logarithm of x plus 4 as the particular solution of some differential equation with initial condition y of 0 equals 8. Okay, so let's go ahead and find out what the differential equation that has this equation as the particular solution. Alright, so to find the differential equation, we'll just simply differentiate this equation, both sides, alright? So we'll differentiate the left side. We just have 1 dy dx, and then on the right side, derivative of secant. Remember what the derivative of secant is. The derivative of secant is secant x tan x. So the derivative of 3 secant x is going to be 3 secant x tan x plus the derivative of natural logarithm of x is 1 over x. So derivative of ln x is 1 over x. And then using the constant rule, the derivative of 4 is 0. Okay? So this right here is our differential equation. Okay, so let's go ahead and box it. This is a differential equation. Now let's verify that this equation is in fact the particular solution to this differential equation that we have right here. Alright, so let's go ahead and verify this. Verification. Alright, so how do we carry out the verification process? We're just going to do the reverse operation of differentiation. So we'll start with the differential equation, dy dx equals 3 secant x tan x plus 1 over x. We're going to use a method that we used before known as separation of variables that works nicely here. We want the y's on the left and the x's on the right. So we have dy equals 3 secant x tan x plus 1 over x, and then we multiply both sides by dx, so we have a dx here, okay? So let me illustrate what I had earlier. You have a dx here that cancels with that, and then we're multiplying this entire side by dx also, okay? Now to solve for y, we're going to integrate both sides. Imagine as though there's a 1 here. So we're going to integrate the left side and also integrate the right side. All right. On the left side, the integral of 1 in respect to y is just simply y plus a constant, but we're going to move the constant to the right side. All right. Now, if we do term by term integration here, we're going to have, this is going to become the integral of 3 secant x. We can factor out the 3 and then just integrate secant x tan x. And then distribute the dx, so the integral of secant x tan x dx plus, now I'll also find the indefinite integral of 1 over x dx also. Okay, so what happened here is we distributed this integral to the two terms and the dx also. Alright, so let's go ahead and find the antiderivative of these two expressions. We're going to have y equals 3. The antiderivative of secant x tan x is simply secant x. The antiderivative of 1 over x is the natural logarithm of the absolute value of x plus a constant, but this is a composite constant. It's a constant from the left side of the equation and the right side of the equation combined, all right? All right, so to find a particular solution, what we're going to use is we're going to use the initial condition we had at the start of the problem, which is that y of 0 is equal to 8. So since y of 0 is equal to 8, that basically means that x is equal to 0. That's your input, and your output y is equal to 8. We're going to plug in these two values into this equation and solve for c, okay? All right, let's go ahead and do that. So we're going to have 8 equals 3 secant 0 plus the natural logarithm of the absolute value of 0 plus c. Okay? All right, so we're going to have 8 equals, secant 0 is the same thing as 1 over cosine, right? So secant 0 is 1 over cosine 0. And we know that cosine 0 is 1. So this is just going to be 1 over 1, which is just 1. So we have 3 times 1 plus the natural logarithm of 0 is 1 plus c. All right. And then we have 8 is equal to um, 3 3 plus 1, which is 4. 4 plus c. And then if we subtract 4 from both sides, we have c equals 4. Now we plug in this c value into the antiderivative we found earlier. Here, we're going to have a final result, which is y equals 3 secant x plus the natural logarithm of the absolute value of x plus, instead of c, plus 4. All right? Now, is this the same thing as what we started with? Let's go ahead and compare. Um, we had 3 secant x plus the natural logarithm of x plus 4. And then we have 3 secant x plus the natural logarithm of x plus 4. Okay, but let's go up here and see. If you notice, in the initial problem, we do not have an absolute value, but we have an absolute value in our solution. So to address that, all we just have to do is take a look at the x value. X is equal to 0, so there's no orientation to our sign there. So that basically means that we're going to be taking the logarithm of a number that's not positive. I mean, that's not negative, which is an acceptable input, okay? So since x is equal to 0, right? We know that the absolute value of x is just simply going to be, it's going to be a valid situation. So we're going to have our final result is going to be, we have the absolute value of x can be expressed as x. Absolute value of x is just x. If we had a negative number here, then we'll have a problem. Then we have to retain this absolute value. But since we're dealing with 0, then we can simply drop this absolute value situation here. So we have y equals 3 secant x plus the natural logarithm of x plus 4. Okay, because of this particular solution, that's why we have the right to drop the absolute value bars from our answer. Okay, and then that's that. That's what we started with, and we're confident that our answer is in fact correct.